Okay, Colin. I think we can start now. Коля, вы готовы?
Да, я да.
Начинайте.
А презентация та же самая или где-то новая?
Сейчас я скину, да, я тут внес справки. Сейчас. Угу. Есть?
Ну, на планшеты не приходит.
Мне пришло.
Вроде есть в чате. Почему?
Есть, пришло.
Так вот, пока не загрузилось.
Я говорю, что у кого планшет, тому не придет.
Да, почему?
Ну, потому что у создателей Zoom такие руки.
На вас не угодишь. Ну, а вы кинете, как умеете обычно, эту ссылку, да? Или это мне надо куда-то кинуть?
Ну, вот Миша переслал, уже сейчас кину.
Ну что, начинаем, давайте.
Начинать?
Да.
Okay. In English, yes?
Yes, please.
Thank you to everybody who come. I'll tell today a story about derivation of tetrahedron equation, which is a generalization of the Young-Baxter equation, and of the most generic known solution to this equation, and how this solution comes from cluster algebras, and how cluster algebra simplify our understanding of it. So I will start from the Young-Baxter equation, then come to tetrahedron equation, and explain how one can be related to another in few various different ways. Then I will tell about cluster algebras and planar networks, and show how we can derive solution, very naturally, solution to tetrahedron equation from the cluster algebras. And if time will permit, I will tell also how this understanding helps us to construct integrable systems, not only with rectangular Newton polygons, which was known for a tetrahedron equation, I think for 15 years, but with any symmetric Newton polygon.
Excuse me, may I ask
yes.
you a short question?
Yes.
If there is some relation between tetrahedron equation and cluster algebras, which algebras take the place of cluster algebras in the case of triangle equation?
Triangle, you mean Young-Baxter?
Yes, yeah.
Good question, I can't answer.
Okay, thank you.
Aleš, may I answer? I suppose it's not a good question, because the tetrahedron equation explains exactly the change from one seed to another. And the stable point...
From what? Sorry, say again. From
seed of the cluster algebra to another. And the stable point of this transformation, in a sense, is the Young-Baxter equation.
No, okay.
Yes.
So what?
This is a simple answer, yes.
I like Cole's answer more.
Yeah, I thought that Alexei is asking some more conceptual answer, and I don't have one.
Okay, excuse me.
So, Cole, isn't the part of the answer that the blocks for the spin chain, which constructed with the Andrei-Marshall satisfy a kind of a limit from the parallel relation, which gives a Poisson bracket.
Yeah, okay. I think this is nothing to discuss now, and it will be clear from my explanations how we can get a parallel equation from cluster algebras and from tetrahedron equation. And if the question will be still valid in the end of the talk, we can discuss it. I think now it's not a good place to discuss this. So starting from Yang-Baxter equation, in fact, I want to start from LLL equation as a starting point, and then we will see how usually Yang-Baxter comes from it. So the starting point is two spaces. We got we have auxiliary space and we have quantum space, and this is just for now it's two just abstract spaces. And we have two operators. One operator is called hermetrics, which intertwine two auxiliary spaces. And another one is the Lux operator, which intertwines, but this means just act now. Quantum space and auxiliary space. And parallel equation, which is a starting point here, is just equation which says that if you have product of two Lux operators along the quantum space, where A is a quantum space. So here we have L1 and then L2. We can permute these two Lux operators using hermetrics and put them into another order. So first we have L2, then we have L1. And our operator, say, permute these two Lux operators. And it is easy to draw this. So we have line which which stands for quantum space, and Lux operators are multiplied in this order. So here we have L2 and then L1 along the line. Then we push this line through the crossing of dashed lines where hermetic stands, and we have after pushing we have Lux operators multiplied in the opposite order. First we have L1, then we have L2. And this is our equation, and we can ask a question: how many solutions can you find for this equation? And for quantum algebra gives us lots and lots of examples and say that actually we can take any two representations of some quantum algebra, affine or non-affine, take two representations and construct both Lux operator and hermetrics from some general prescription, say universal hermetrics and something like this. And if we found some solution to this equation, we just using this equation, we can multiply it by r to the minus first from the right and get like this form of this equation, and take trace over both auxiliary spaces and find this very simple and important formula that traces of Lux operators taken over auxiliary spaces are commuting. And if you have spectral parameters, this gives us lots and lots of commuting Hamiltonians. And in fact, usually this is enough to prove some kind of integrability for system like lattice system or quantum field, in quantum field theory, some integrable system. So this is a result just of parallel equation. Now, how starting from parallel equation, how Yang-Baxter equation come, which is another equation which use hermetrics only. So I have to show some drawing here which illustrate what I want to say. So let's take now 3 Lux operators and multiply 3 Lux operators. So we have here L3 first L operator acting in some quantum space A, and third auxiliary space, then second, then first. Now we can permute these Lux operators to the opposite order. So here we have Lux operators in the opposite order. First, second, third. We can permute them in 2 different ways. So the first way is the following: take first these 2 spaces and act by R matrix. Then using parallel equation, you can push this line through this crossing, then multiply here and push again, and here push again. So we get this equality. This is just parallel equation applied 3 times. We can also do the same in the opposite order. So we can first take where is my mouse? I see. You can first permute in this space, then in this space, then in this space, and actually you get the same result. You have L1, L2, and L3 permuted, but this is like different expression. Just we have 3 matrices here and 3 L matrices here, but like the multiplication is different. So here I just written the same expression, and we again can multiply by the product of our matrices from the left hand side and right hand side to get form which is similar to this form of parallel equation. But here we have 3 matrices, so the statement that 3 Lux operators can be permuted using 2 different adjoint actions of 2 different operators. One is constructed from 3 matrices, another also from 3 matrices, but in opposite orders. And now we can not deduce, but make an assumption that not only adjoint action on Lux operators is the same, but also the product of these matrices are the same. So we deduce that in some sense Young-Baxter equation is associativity condition for the action of R matrices on Lux operators by permutation. Any questions here? So I finish with Young-Baxter and parallel equation. Okay, if no questions, I go to the tetrahedron equation. And please note that here row of spaces V and F is in some sense similar, but in some sense it's different. So be careful. So now we have again 2 operators. First operator is L, which now act in 3 spaces, 2 of which are V, and the third is F. And R operator, which act in a product of 3 copies of space of type F. And we write, I think Zamolodchikov or some other clever people write this equation, which is similar in some sense to parallel equation. So now we have product of 3 L operators and 1 R operator, which is equal to the product in another order. And if we take a more careful look to these pictures, we see that in fact we have a triangle similar to the triangle which we saw in Young-Baxter equation, made from dashed lines, which are V spaces. And on the right, we also have such triangle. And again, like in Young-Baxter equation, the spaces or say the lines are permuted. So we have as a base for this tetrahedron, we have Young-Baxter equation, which is triangle made from dashed lines. And on the top of this triangle, we have R matrix. So I will say that we have plane in which we have Young-Baxter equation. And we also have R matrix which first act from the bottom of this plane and then from the top, on the right side on the top of this plane. And it acts on this additional space which is located in the normal direction to the plane in which these spaces exist. So this is a tetrahedron equation. Is the picture clear? I understand that it's hard to see all the orders, compare all orders of these operators and the drawing, but probably some expressions.
So, for example, is it correct that normal direction is rotated from the left picture to the right one?
Why rotated?
I'm just trying to imagine this.
But if I can draw coordinate plane, so here it's like this.
No, it's the same. Yes.
Here it's also like I can draw it here. So
sorry.
Yes.
I am a bit puzzled because you are using L sub 1, 2. What is this operator? Does it mean that it acts on the tensor square of V?
Yes, L acts on product of three spaces, two of which are we label by numbers, and third we label by letter.
Ah, yeah, I see. Mm-hmm. Yes.
So I proceed. And we can make the same trick which we made with similar trick to those which we made when we constructed Hamiltonians, but now we have like more spaces and something more interesting happens. So I want to move this R matrix from the left-hand side to the right-hand side of this equation, and I just multiply by R to the minus first and get product of three L operators on the left and product of three L operators on the right, but under the adjoint action of this R operator. And now we can interpret this matrix acting in three spaces in the tensor product of three spaces as a matrix, like matrix along this this tensor product, but with values in endomorphisms of the third spaces of the third space. So in the following, I will use this interpretation that a matrix is matrix, but now with values and operators, in the opposite to the case of Young-Baxter equation, which where like L operator was also matrix, but it was matrix with indices in one space. Now it's matrix with indices in two spaces. And if I take this point of view, I can interpret right-hand side of this equation now as again product of three matrices, but now like operators which stay inside this matrix are different. They are different by conjugation. So in a sense, this is again Young-Baxter equation for some R matrix, but now this R matrix is not like matrix which depends only on some commuting spectral parameters. But now this is a matrix which depends on operators, and these operators on the left-hand side and right-hand side are different. But as this is conjugation, the relations among these operators have to be the same on the right side and on the left side, because conjugation doesn't change relations among operators. This is an important point, and in fact we will be using in the following mainly and probe mainly this equation. And important point, as we will be mainly dealing with classical limit of tetrahedron equation. In this form, we can also say that this transformation which was made is canonical transformation of some Poisson algebra. Okay. So now the analog.
Mykola, I'm sorry.
Yes.
It is a Poisson canonical transformation for which Poisson algebra? For one variable v, for three variables. Could you make more precise?
Good question. And in example, it will be clear. And general answer is that in this form we can think that we take some algebra of operators which act on the space F, and we want this, like this can be not entire algebra of endomorphism of this vector space, but some subalgebra. And we say that L depends on some generators of this algebra. And in classical limit, we take classical limit of these generators and get some Poisson algebra. Is initial algebra was in some sense close to the Lie algebra. Did I answer?
Okay, it's better to wait a little bit.
Okay, I hope this will be clear in example.
Mykola, sorry, Mykola.
Yes,
sorry,
yes.
I don't understand. So what this passage from second line to third line, it is what? Assumption
from
or
this,
result?
From this to this?
Yes.
This is just this is just interpretation. So here we have, for example, take this operator L12, A. This is this is operators which acts in three spaces, in space 1, 2, and A. Now I say that this is operator which act in spaces 1 and 2. This is matrix by this spaces, but it has its values in operators which act in the space A. This is just interpretation. So I can say that endomorphism of three spaces is are equal to endomorphism of these spaces times endomorphism of this space. And if I take this point of view, I can think that on the right side, the joint action of the matrix, it transforms algebra, it conjugates as this matrix acts only in spaces A, B, and C. This is just some conjugation, some operator which acts by conjugation on tensor product of three algebras of operators on space F.
Wow, it looks still that there's some condition on L.
Condition on what? If condition on what?
Oh, well, you start as looking for the first equation. It is clear that R somehow change order, yes? Because what is written in the first line of L operators. And now you reduce it only to action on this space of endomorphisms of F. So it loses some kind of property.
Let me say it this way. Take some matrix element. Take some matrix element over spaces 1, 2, and 3. Let spaces 1, 2, and 3 be two-dimensional. So this is just some equality of 6 by 6, 8 by 8 matrices, which are valued in some operators. and conditions that left-hand side is equivalent to the right-hand side is a condition that some matrix element is equal to some matrix element, and matrix element on the right-hand side we get from similar matrix, which is here, but which is conjugated by some non-trivial operator.
So we can suppose, for example, that these are just, for example, matrix elements of L12, L13, and L23. There are some generators of endomorphisms, and V prime is exactly this action of our matrix on V. So we could write just add R acting on each matrix element of matrix L.
Well, okay, Pasha, but if you change, so let's take the third line, yes? And let's apply this R minus 1 from both sides. Then as it is written, there will be no change of order of L operators.
But
This
non-trivial
R will
statement.
go inside and
you had to ask this question about the first equation, because already this was some non-trivial statement that there is such a matrix that and there is such an operator that they satisfy RLL relation. It's non-trivial statement, and then it is said that it is equivalent to the third line.
Well, it seems to me that there are some conditions here. Okay, sorry, maybe.
Andrei, of course, there are conditions. But what Koля told you in the middle, you have three matrices which depend on some variables V, and the product in one order is equal to a product in another order with this V being changed. Of course, it is condition. It's not for arbitrary matrices and arbitrary variables. And as I understand, very
well. But if I look for the fourth line, I don't see this condition on L. I would have the result without change of this fourth line. Yes, I would get the same result with the same order of L matrices.
Order of L matrices and order the appearance of R matrices is different. So this is just equivalent, the first line to third plus fourth.
Yes, but of course there is of course non-trivial condition that these three L matrices satisfy RLL equation for some R. It's not, of course, for any L matrix.
In fact, the very strong restriction is that the relations among inside these algebras are preserved by some transformation. So this is a strong restriction that the transformations of these V's is conjugation, not any automorphism, but conjugation by something. This is also very restrictive.
Okay, sorry, maybe I have to. Okay, so,
in example, it will be clear, I hope.
Okay, thank
you. So here we already have something which looks very much similar to Young-Baxter equation, but now we go further, and here we have again something very similar. So, but another. So here we have what is called a functional tetrahedron equation, and this is like Young-Baxter equation. This is equation for similar objects for these R matrices, and it comes in a very similar way how like Young-Baxter equation came in the case of RLL equation. So let's take, but now not product of 3, but product of 6 L operators, and here the picture which illustrates this formula, and here we look from the top on the plane where V spaces act, and I just omit the spaces which act in plane perpendicular to the plane of these spaces. So I do not draw F spaces here, but put letters which indicate names of spaces corresponding to crossings. So we can take product of 6 operators and permute them to this form, again by application of this tetrahedron equation. So, for example, we can put think that this is a base for tetrahedron which we glue from the top on this triangle. We put our matrix from the top, and using this R matrix, we can push one line through another. For example, this line through this crossing B. But by application of 4 R matrices, we can move to this picture. But we can do this in 2 different ways again. So in first way, for example, we first act on triangle CEF. So this is this triangle. And in another way, we can first act on triangle ABC. So this triangle. And again, this equation completely follows from this. This is just this equation applied 4 times. But we make additional assumption that not only adjoint action of these operators on L operators coincide, but also operators itself coincide. And we get this equation where 4 matrices on the left side and 4 matrices on the right side are involved. And the notable thing is in the same way how in the case of RL equation, we Young-Baxter equation has the same form or the same graphical representation as RL equation. Here, completely the same thing happens. And in fact, I do not draw it here, but this functional tetrahedron equation on R matrices have completely the same pictorial form as initial tetrahedron equation. So this is again this such picture, but where all lines are solid, and on all crossings we have R matrices. So this is again pair of 2 similar equations, and one.
Mykola, why you call this functional equation? Why not just tetrahedron?
I don't know. You should better ask Sim Kashayev. This is not my idea. I don't know. This is the name. Probably because they was looking for ansatz in some functional forms. So this was considered as some functional equation on matrix elements of these R matrices, probably.
But this is in quantum, in product of quantum spaces, right?
Yes.
Maybe because these spaces are infinite dimensional.
No, it's just a finite dimensional equation for some metrics. No, okay, it's just terminology.
Igor, it's not a matrix, it's an operator in quantum.
Yeah, I understand.
I don't know. This is just a name. Okay, so are there any general questions on these equations? And I will go to examples. Okay, if no questions, as I understand, this is the most general, in some sense, the most general solution which covers in limits all other known solutions. Probably I make a mistake, but by such strong statement, but this is my understanding. and this was solution probably first found by Sergeyev, then developed together with Bozhanov. And as I said, we can consider like L matrix as a matrix with values in some operators. And in this solution, the V space is two-dimensional, so L is 4 by 4 matrix. And this, say, quantum space F is infinite dimensional and is a representation space of this Q oscillator algebra of Q oscillators. So the main relation is this. This is deformed oscillator algebra. So the space F is infinite dimensional, and you can think that in some sense this is algebra of polynomials on X. But as I will not need a quantum solution in the following, I will not deal with quantum world, but with classical world. I present here only classical limit of their solution. So in classical limit, this algebra of oscillator becomes algebra of like just Poisson algebra with this relation. So we have two Casimirs, lambda and mu. We can assume them to be just numbers. And the main relation is this. So Poisson bracket of x and y is equal to k square, where k square is 1 minus xy. Not the most natural algebra which you can imagine, but it is so. And the solution which was provided by Bozhanov and Sergeyev have this simple form. So there is some diagonal part and two out of diagonal matrix elements, and it's quite simple. But such simple solution have to.
Sorry, Kolya, I just forgot where lambda and mu are on top. In quantum.
Here.
Yes, here. Where
you can think here.
No, but why you said 2 Casimirs, not 3 Casimirs, not 4?
Because solution depends on two complex parameters.
Just because this matrix has 2 parameters.
Yes. But in fact, this is quite. You can just drop these parameters. In fact, and sometimes they act in this way because this is just. If you see, this is just conjugation by some diagonal matrix in one space. So this is mu is you see that mu stay in just in second and fourth row, and lambda stays only in third and fourth column. So you can drop. In fact, you can drop these numbers, but for our purposes, it's reasonable to preserve them. So this is simple. This is simple matrix, and quite simple algebra, but it has to satisfy quite complicated restrictions, and the restrictions are the following. So we write this equation, which we derived earlier.
And what is R operator in the previous slide?
Good question. The R operator is canonical transformation. As I said,
canonical transformation of this Poisson algebra, right?
Yes. And here this transformation is written. And in fact, very non-trivial and restrictive check is that this transformation, which can be completely derived from this equation. So this is just system of 64 equations, very redundant. And firstly, this system have solution, and this solution is written here, very complicated transformation of variables. And the major complicatedness is like hidden here in this transformation, which is highly nonlinear. And the second and very strong like check on consistency or non-triviality, that this transformation is canonical. And this transformation is canonical means that x's and y's and k's with different indices have 0 Poisson bracket. So, for example, xa prime with kc prime or with kb prime have a 0 vanishing Poisson bracket if we compute brackets using like brackets on non-primed variables.
Is it some known discrete time integrable system?
I think that this system was introduced in this paper, in their paper in 2005, I think. In some sense, this is related to, but not classical limit. If you take not classical limit but a limit to some roots of 0, they identify this with some systems with star triangle integrability relation. So if you, yes, there are finite dimensional solutions which can be obtained from this solution by limit q to the root of 0, and this is related to star triangle, which was known, I think, a long time before their work.
Mykola, could you give some comments about the Poisson structure? Your initial definition of the tetrahedron equation was given without any notion of Poisson structure. What is the conceptual meaning of this additional symmetry, additional structure?
Conceptually, I just can say that like at the point when we came from this equation to some equation on endomorphisms, it is natural to assume that endomorphisms, that like algebra of endomorphism acts in some representation space. And as we know, like this is fact of nature. I don't know that very often like representations are representations of some Q-deformed algebras. And if algebra is Q-deformed, it have to obey some classical limit. And Poisson algebra
of a classical limit. Thank you.
Yeah.
Kolya, I don't understand what you say about representations, because it looks like you had quantum space, yeah, with some commutational relations, and what you say is that the Poisson algebra is just a limit of this quantum algebra.
Yeah, yes.
A classical limit.
Yes.
No representation of anything in general.
But before classical limit, we got representation of algebra of oscillators of this algebra.
No, okay, yeah, I see. Okay, if you by representation, you just mean representation of this quantum algebra.
Yeah,
okay.
In the same
and
sense.
The question, and just the question that totally you have a product of 3 such spaces. So just just the product of 3 identical Poisson structures.
Yes. And now I can like say a few more words on quantum groups and relations of this tetrahedron equation to like usual quantum groups. And there is like I can say motivating consideration, and the consideration is following. Space V is 2-dimensional space, and like if you want this to be a representation space of something, we can assign some character. So let's say that this 2-dimensional space have character 1 plus x, and if you as far as we will have many spaces of this V type, we have index I for like just to distinguish identical spaces. And the observation is the following, that if you take like character of tensor product of n of such spaces, so just product of 1 plus x1 times 1 plus x2 up to 1 plus xn, and you expand this product as a sum over like degrees of x, and here is the first degree, here is the second degree, and here is the nth degree, and it's very easy to see that these combinations are just characters of fundamental representations of GLN. And also the same thing happens with another space, with space F, which is infinite dimensional, and as I said before, like it's infinite dimensional in one direction. And if you write, sorry, here I have to write x also. And if you take again character of this space and multiply n such characters with different letters, you get also sum, but now infinite sum, and now not over fundamental, but over symmetric representations of also GLN. And this consideration is consistent with the following claims. And this claim can be directly checked by computation. The claim is following. Let's define such Lux, now I call this is truly Lux operator, which is product of these tetrahedron Lux matrices by one two-dimensional space, by two-dimensional space 0. And if I take trace of this product, I get some operator which act in 2 to the n dimensional space, which is tensor product of 1, 2, and so to n. And also it acts in infinite dimensional, n times infinite dimensional space, which is tensor product of a1, a2, and so to an. And the statement is that this big Lux operator, it decomposes this 2 to the n dimensional space. It indeed decomposes into sum, direct sum of these spaces. So this is block matrix, which have only diagonal blocks corresponding to like these fundamental representations of GLN. And these blocks, which are now operators in quantum case, it is operator, but in classical case, it's just some Poisson variables attributed to spaces 1, 2, and n. And those matrices are Lux operators corresponding to case fundamental representations of UQ or GLK in quantum space, or in classical limit, these matrices satisfy classical Young-Baxter equation with classical trigonometric R matrix here. And role of play of spectral operators is played by those operators which I plugged in the matrices. And also similar claim holds, and this was obtained, I think, later, probably in 2012 by Mangazeev and collaborators, if I'm not wrong, that similar holds for R matrix, and such operator gives us R matrices in products of all symmetric representations of GLN. And this is how why this solution of tetrahedron equation is called quantum group-like solution, because this is like mother solution for all finite dimensional of many finite dimensional R operators for quantum group GLN. And in fact, by Sergeev, it was also obtained that if you take not trace here, but if you take some very particular matrix elements, so if you multiply here by some two-dimensional vector and here some two-dimensional vector, you obtain Lux operators for B and C series of quantum groups. So it's very consistent. Okay, so questions here, because I finish with Lux operators and go to cluster algebras.
Sorry, maybe I missed. This L operator depends on the on the variables which acts on this F space, which are defined by V. So this they form algebra like quantum group. What should, I mean, function of quantum group? What should I think? Where are they in this formula for bracket?
I think this is like embedding of torus into quantum group. So this is some chart parameterized by torus inside quantum group.
Quantum group has dimension like n squared, but we have like 2n. So this is like some cell?
Yes, this is cell.
Why just cell? Where is the full quantum group?
This is like, as you will see, this is like with quantum, with cluster algebras. So this is one cell, and in fact this Lux operator is cell corresponding to XXZ spin chain. And you can also try to construct the largest cell, and this is also possible, but this will be more complicated product of Lux operators.
Ah, I see.
I'm probably not ready now to draw this the largest cell, but at the end probably we can discuss it when we come to like symmetric Newton polygons at the end. Okay, any other questions?
I missed the definition of the spectral parameter lambda. What does it mean?
Yeah, this is a good question, and now I think I will not give a precise answer, but not precise answer is this spectral parameter lambda here in Lux operator. It comes from this parameter lambda and mu. From this
Is it related to the affine quantum group or to the ordinary one?
It's related to the ordinary one, but like R matrix with Lux matrix with spectral parameter. So yes, you're right that there must be somewhere affine quantum group, but I don't know where. So this is like limit where only like only classical, only non-affine with spectral parameter remains.
Okay, thank you.
Result of evaluation homomorphism, something like this.
Thank you.
So you're talking. So from my question, you're talking about cells in loop quantum group.
Yeah. Yes. Yeah. You're right.
Perfect.
So if you say about a cell in a loop quantum group here of A type, so and you say that more general cells correspond to some general Newton polygons. So what is the Newton polygon here?
Like in our paper.
But why? That I don't quite understand. So what you should change? Yeah, then. So you say that here it's rectangle, yeah?
You push me to the very end. Yes.
Yeah, it's very good. I see. And if I push you now back,
okay.
So where are here the parameters of the polygon? Just missed.
What do you mean by you mean?
I thought it was formula like product of simple reflections. All of them are different, no?
But then the polygon, as we know, is different.
No. This is not product of simple reflections.
So it's not Coxeter like it naively looks like.
I understand
that's what you say.
No, I think that this is an additional generator which is not contained in double affine wave group.
And where is it here in the structure of your product?
Where is this? Is
yes.
It is not contained in double affine wave group, so we cannot write it using generators of it. This is some additional.
Okay, can I ask you differently? So if you show me this, my love, or your lovely rectangle, so one side is n, and what is another side?
1.
Just one.
No, because if you take trace over spaces 1, 2, and n, it will be 1. If you multiply more than one such operator, you will get 2 or 3. So to say differently, this is product along Dynkin diagram. And this was the point of Pazhanov and Sergeyev, that like tetrahedron equation, it refines a quantum group and provides us with some Lux operator, which in sense act along Dynkin diagram. Because if you take different number of operators which are multiplied here corresponds to the length of Dynkin diagram, like of the algebra, which corresponds to the Lux operator, which is obtained by taking trace. So now I go to like perfect networks and cluster algebras. And sorry, I will be quite fast. So perfect network is oriented graph on now on a disk, and graph vertices of this graph can be colored into 2 colors, black or white. And this graph is oriented, and orientation is so that that black vertices are those which have has precisely one incoming edge, and all other edges are outgoing. And white vertices are those which have one outgoing and all others exactly one outgoing. So there can be no 0. And all others are ingoing, like on this picture. Technically, it's convenient to say that on the ends of these edges, outer edges, and on the middles of internal edges, there are some gray vertices which are not, however, drawn. And another part of data which is attributed to perfect network is weights. And we say that there is some weight which is attached to each half edge. So each edge connecting black or white vertex and gray vertex. So half edges have some weights. And we also use following notations that the sources on the graph denoted by I is the set of boundary vertices which are outgoing, and sinks are boundary vertices which are ingoing. We also, as far as we have some weights attributed to edges, we can consider some partition functions. And main partition function is partition function of flows, and flows are just sets of passes on this graph which are not non-intersecting and which are oriented like along the orientation of graph. So on this picture, for example, we have the same orthogonal graph, and orientation also is drawn here. And here we have all possible flows on this graph. So you cannot draw any other set of passes on this graph which are not non-intersecting and which are oriented along the orientation of the graph. And we say that we can fix some subset of sources and some subset of sinks, and consider only passes which connect these sources and those sinks. And we say that partition function of like flows with boundary condition, or partition function of flows from A to B, is sum of weights over all such passes. And a very convenient object which allows you to encode like weights of of passes and encode these partition functions of flows. And the most important thing that you can easily like glue these networks and like compute partition function of flows on glued networks by partition functions on parts is transfer matrix. And transfer matrix is, as usual, is some matrix which acts from the space which is C2 to the power of the number of things, to C2 to the, of sources to the C2 to the power of things, and each matrix element is corresponding to partition function of flows where only some things are like involved and only some sources and only some things are like contain ingoing or outgoing paths, and all other things and sources are not involved. So like continuing with our example, here is written a transfer matrix of flows for this example. So let's take some matrix element. For example,
Because a stupid question. Why is C2 to the power of I? Is it why C2 not some other space?
Because we have path or we don't have path. So let's consider some example. For example, diagonal example, gamma 3, gamma 4 to the minus first. Yes, what this matrix element corresponds to here? It corresponds to this like flow, and only one flow with such boundary conditions. And you see that only one source contains path. So source of the number 1 and source of number 2 is not involved. And also thing of number 1 prime is involved and 2 prime is not involved. And it is like set of involved or not involved sources and things correspond to like position of this matrix element in tensor product.
So what are gammas?
Now, yeah, good question. Gammas is some, I said that on perfect network, we attribute weight to some half edge, but it's not convenient to keep all these weights. And I keep keep in mind and have notation only weights on some long passes. And in fact, we can parameterize all flows on this graph using only these 4 passes.
Thank you.
It's clear, yeah?
Yeah.
Okay. And the final step, yes, is Poisson bracket, and this Poisson structure was, I think, introduced by Gehman, Shapiro, and Weinstein first, or yeah, I think so. And it is very simple, in fact, and you can write it in this way. But to make it short, I say that if you have like let you have 2 passes, say gamma 1 and gamma 2, and let you have variables corresponding to these passes, or just product of half edge with proper orientation which contribute to this path. And Poisson bracket of variables corresponding to these passes, it's how is it called? Logarithmically quadratic. So gamma 1, gamma 2, and again on the right you also have W gamma 1 and W gamma 2.
Logarithmically constant, maybe, yes?
Sorry, yes, logarithmically constant, yes. Yes, thank you. And here you have the number, and this is half integral number. And this number can be computed in the following way. You take all the vertices where these passes gamma 1 and gamma 2 intersect, so common vertices for these passes, and sum over contributions, as it is written here. You sum over all contributions of these vertices, and you sum, if the vertex is black, you sum with sign plus, and if the vertex is white, you sum with sign minus. Sorry, and the number which you sum is +1 if passes intersect like in a positive direction. So if you have first gamma 1 and if you have first gamma 1 and then gamma 2, you have 1/2. And also gamma 2, gamma 3 have 1/2, and also gamma 3, gamma 1 also have 1/2. And this form is skew-symmetric, so for gamma 2, gamma 1, you have -1/2. Probably it is good to look at this example. So Poisson bracket of gamma 1 and gamma 2 is equal to -1/2, because gamma 1 and gamma 2 have only one common vertex. This vertex is common for them. And this vertex is white, so we have -1 here. And we have gamma 1 first and then gamma second along in clockwise direction. So we have 1/2, not -1/2, but 1/2. And altogether give -1/2. And similarly, you can easily see that for others, the brackets are similar, and these passes do not intersect, so their Poisson bracket is 0. And now, so questions on Poisson brackets? Okay, so now the first result of our Andrei Vladimirovich. Okay.
Well, just maybe do you have to check something for these Poisson brackets, or
for this?
Yeah, for this.
Yeah, yes, right. Thank you. Right question. Sure. You have to check that product of all variables corresponding to one vertex. So product of gamma 1, gamma 2, and gamma 3, it have zero Poisson bracket with all these gammas, all these single gammas. So as a sum of these passes is 0, because if you go here, here, and here, you come to the initial point and you passed all the half edges 2 times in different directions. Thank you. So this is a condition, and it is surely satisfied with some notations.
And since you have only 3 valent vertices, this is just the only condition.
Yes, and I think if you have more than 3 valent, you also, this is the only condition.
But for vertex of each type, yeah?
Yes, for each vertex, yes. Mm-hmm. Thank you. So our claim was that this solution of Bazhanov and Sergeyev, and this was initial observation, that this solution of Bazhanov and Sergeyev is precisely equal to transfer matrix of these passes on perfect network. And a priori, this was not clear at all, and there is no reason for this to be so. Up to some conjugation by very simple factors. So this is just like a flip of spins and permutation of spaces, but this doesn't matter. And in fact, they're equal, and variables are equal in this way. And Poisson brackets are also consistent, which was first non-trivial check of this correspondence. And a priori, there were no reason for Poisson brackets to be consistent, but they were, and it was surprising. Okay, so this was Lax operators, and now we have to go and to identify what is tetrahedron equation itself. I mean, like product of 3 Lax operators have to be equal in some way, because we know this from tetrahedron equation, to product of 3 Lax operators in another way, and with the different variables, with transformed variables. And in fact, if like this theory is consistent, we have to recover these complicated formulas from some structure related to perfect networks and their transformations. And luckily, there is some amount of transformations of network. And I will briefly outline what the transformations are. So,
Mykola, excuse me.
Yes.
How you came to this expression for Bazhanov-Sergeyev solution in terms of
This what?
No. You just claimed that the Bazhanov-Sergeyev solution is just transfer matrix for foregone. There should be some reason why you looked at the beginning.
As usually, this was no coincidence. In fact, I was presenting our work with Andrei Vladimirovich on CQIS workshop 2 years ago, and I written and drawn expression for Lax operators of XXZ chain from cluster algebras. So this is kind of this expression. This was kind of this expression, and on the same workshop was Yegor Zinkevich, who very excited of the tetrahedron equation and who knows that from Bazhanov-Sergeyev Lax operator, you can construct Lax operator for XXZ classical spin chain. And he asked me if these two things are related, and I very fastly checked that indeed Lax operators coincide and Poisson brackets coincide. Just on workshop we did it, and then on the same workshop Pasha Gavrilenko found transformation of this product of 3 Lax operators as a composition of 4 mutations. So just by coincidence. So now to present transformation, we met some technical complicated technical problems because we have to deal with these corner variables which are the most suitable for our purposes, and we had to formulate all usual network transformations in terms of these corner variables. And formulas like ansatses which we looked for satisfied 3 conditions. So first, if you transform, for example, this is a simple transformation, we transform this network to this network, and we require that transfer matrix of flows has to be preserved. Also, we require that Poisson brackets have to be consistent, and formulas which express transform Poisson variables from the initial have to be consistent with Poisson brackets on both sides. So this has to be a Poisson map. And also all basic symmetries of this graph, like reflection symmetries and so on, have to be respected by these formulas. And for example, for this simple flop or to move transformation, you can find such formulas. And in fact, these formulas are the only formulas which satisfy this, in the class of monomial transformations. These transformations are the only transformations which satisfy all the requirements. They are monomial, but they contain some fractional degrees, in fact. And also same transformation for white vertices, and this is a bit different because colors are different, so signs in Poisson brackets are different. And the least trivial and very complicated transformation is called for move, and which is responsible for mutation in cluster algebras, and it is also called spider move or urban renewal or other names. And in fact, we have to map these 12 variables, to new 12 variables, satisfying all the requirements. And it was found that there is 3 parametric family of such transformations. So for arbitrarily for arbitrary alpha 1, alpha 2, and alpha 3, this transformation of variables, it satisfies all requirements. And for those who are familiar with cluster algebra or spider moves, I say that here they can recognize usual non-monomial factor for these transformations. And if you take like the thing is that we deal here with like corner variable, and if you map this, like multiply these corner variables to obtain phase variables, like A1 times D1 times C1 times B1 is path which surrounds this phase, and this is what is called phase variable. And if you multiply this and also multiply A3 by B3, and find all these phase variables, for the phase variables, this is usual transformation of mutation. But we can refine this transformation using corner variables in such complicated way. And it appeared that all these three deformations are necessary to obtain right answer. And here I have to say that I said that phase variables are corresponding to some cluster algebra, and here I can briefly outline what I mean. First, sorry for many definitions, but first we can define X cluster variety, and this is variety covered by some algebraic torus, and all toruses have the same dimension. So, and we can the main objects are X cluster variables, which are coordinates on these toruses. And these coordinates have like such Poisson bracket, which is logarithmically constant. And this bracket is defined by epsilon, which is a skew-symmetric exchange matrix. And it's convenient to draw such matrices using quiver. And for example, for this four-gonal block, we said we can define phase variables, and Poisson brackets of these phase variables are encoded in this quiver. And if you have vertices of this quiver are corresponding to faces of this graph, and if you have edge, this like solid edge, this means that the Poisson bracket of this variable with this variable is goes with coefficient 1. And if you have dashed edge here, this means that the Poisson bracket between this and this phase is 1/2 times their product. And this is how this epsilon matrix be constructed. And the rule is that you draw half like a gray arrow along each black vertex in clockwise direction, and along each white vertex in counterclockwise direction, and then you put all vertices together and get all edges together, all arrows together, and get this quiver. But in fact, we will not need strongly this, so you can forget that this is not much important for our consideration. And what is important and what corresponds to this transformation is a so-called mutation, which is formally for formal X cluster variety can be defined by a pair of formulas. And first formula is how variables are mapped. So X prime, which is a new variable and which is coordinated on some new chart, which is glued to a previous chart by this mutation. So new variables are obtained by these formulas. So we invert variable in which we make mutation. Mutation is made here in vertex I. And we multiply by some factor all vertices which are adjacent on quiver to the initial vertex. And in fact, claim which relate this formal story about cluster algebras and our story about flows on perfect networks is that we can consider phase variables of a network. Phase variables are variables corresponding to passes surrounding phases. Their phase variables are corresponding to coordinates in X cluster variety. And this is like cluster part of this story. And our statement is
So sorry, Cole, about this last statement, yeah, about this D and G, whatever it means, it's actually after you glue this completely, yeah? Because if before this gluing, when you get torus, there should be some set of frozen variables as well.
Yes, you're right, yes, and yes.
Thank you.
And now, just not to annoy you with this cluster algebras, the statement like which is considerable and provable is that this tetrahedron transformation, which maps product of 3 Lax operators to the product of 3 Lax operators in opposite order, can be performed by sequence of perfect network transformations by 2 moves and 4 moves. And the main component of this transformation is composition of 4 mutations. And here I drawn a detailed picture. So how it happens? We have this perfect network, and you perform 2 move here and 2 move here, and this change order of these intersections interchange, and then you can perform 4 move here, then you perform pair of 2 moves here, you get 2 rhombus, and you again make 2 mutations at this rhombus or 2 spider moves, and again pair of 2 moves and 4 move, and then again pair of 2 moves, and you obtain product of the same square but in a different on the different lines. And this is pictorially, it's easy to see that this corresponds to this Yang-Baxter equation, but Lax operators depend on path variables, and path variables are transformed by these transformations. So this is like Yang-Baxter equation, but the variables which operators depend on are transformed by the transformations. And as I said, each transformation is canonical in sense. So the overall transformation is also canonical. So it maps Poisson algebra corresponding to this to Poisson algebra corresponding to this, and the brackets are correct. For example, you can check first that on phase variables, it's simple check that you can perform this transformation phase variables, and 0, x1, and so on are drawn on this picture. This is our phases. First phase, second, third, and so on. And total transformation of phase variables is this, and it's not simple, but I have to say that in fact this pair of Weavers and this composition of cluster transformations, and it appeared when we was preparing our paper to publication, that these transformations was obtained already by Yamazaki, who also studied this quiver in similar context, but in the context of star triangle relations. And from the point of view of quantum field theory, integrability in quantum field theory, our consideration is corresponding to n = 1 super Young mules in 5 dimensions, and his consideration was related to superconformal and indices of superconformal series in two dimensions, in n equal to 2 sigma models in 2 dimensions. So very different contexts, but the same cluster algebra, and in fact the same transformation, surprisingly. And we still do not know explanation of this relation. And finally, you can find transformation of corner variables, and this requires some additional gauge transformation, or say multiplication by diagonal matrices, but this also can be found and checked that anything is consistent. So this is indeed, and this transformation is, so this transformation of gamma or corner variables by this identification of variables, of tetrahedron variables and corner variables, can be checked to coincide with this transformation of tetrahedron variable. So this is exactly the same transformation. So here is the end of the main story, I think. And now we have 26 minutes, and now questions on this main part.
Maybe it's not on the main part, but you presented in this network form solutions of Bajanov-Sergeev. There were originally solutions found by Samolotchikov himself. Then there were solutions found by Karipanov, and Dima Talalayev was involved. How they are related to the class of solutions you described?
I hope, I think that Dmitry can explain better, but my understanding is the following, that those solutions which was obtained by Samolotchikov and then Bajanov-Baxter, they are corresponding to they are corresponding to limit q to the root of unity of this like representation. So if you take not infinite dimensional representation of this algebra, but n-dimensional representation of algebra, if q is nth root of unity, you get those solutions by Samolotchikov and Bajanov-Baxter. About Karipanovs and Talalayevs, I don't remember. Probably I forgot.
Okay, thank you. But these solutions have no classical limit, so you cannot compare to
yes,
networks.
You're completely right, and this is another good evidence of consistency of this series, and the following. Solution is finite dimensional and quantum, and in cluster algebras we also have simple quantization of cluster algebra, where Poisson bracket is replaced by Q commutation relation. So I can draw probably this. So, for example, in cluster algebra, we have relation of this kind. This x and y is, okay, let's write A and B, is equal to, for example, AB, and this can be simply quantized to such quantum torus, and this is very consistent, and quantum cluster algebras are also very well developed. And it is known that on classical level we have mutation mu, which is canonical transformation, And on classical level, or sorry, on quantum level, we have like conjugation by quantum de logarithm. I would be wrong. I mean, this is pictorial formula. I write A here. This is mistake, but just to illustrate. And quantum de logarithm is product of k from 0 to infinity of 1 minus q to the k. Okay, let it be c to the c. So this is conjugation. And this is how mutation can be performed. So you perform all your cluster variables. You conjugate by all your cluster variables by quantum de logarithm, and you got new formulas which contain those factors which we have to get after mutation. And in fact, sorry for showing like paper, but this is quite far from my talk. But if you take a look into paper by Sergeyev on quantum solution, you find in the root of unity, this was about roots of unity, you find that the formula for R matrix, which he found, it consists of a product of four functions W, and these functions W are in fact cousins of quantum de logarithm, but in the root of unity. So in fact, this gives hope that by taking limit to the root of unity in cluster algebra, you replace quantum de logarithm, which you have to conjugate by some functions in root of unity, which are these functions.
Sorry, Kolya, and where is here root of unity? Because product is finite.
It's written not here, but I think on the here it's written here. So Q is root of unity. Here is written, and product is finite. Yes.
Mm-hmm.
So this is another evidence, and in paper by Sergey. No, this is okay. So I will not show more papers, but in paper by Sergeyev, he got all. In paper by Sergeyev, he got quantum de logarithm itself, not in the root of unity, but quantum de logarithm.
Thank you. Thank you.
Mm-hmm. But we had, but we didn't make this job with quantum cluster algebras because of some technical problems, and this is long story. Okay, any other questions related to this part? Okay, so I think I still have 20 minutes or something like this. Yes. Or I have to finish by then.
But your plan is not covered yet.
Yeah, I know, but this is a good point to finish. I can say a few words about like relation to
maybe we shall
continue maybe
once more.
Yeah.
Once more.
I don't like rushing at the end of the talk, especially if the talk is so exciting. So what do you think, Andrei?
Well, I would prefer to listen Kolya once more, but well, I'm not a generic person in the audience in any case, so it's better not to ask me. Yeah.
Let's see me as a generic person. Let's have another talk.
How you say? Okay.
If Коля not object.
Yeah, but why? I'm okay with this.
No, no, Koля was objected for this particular time, for this particular Monday, but not for anyone, not for anyone different.
Continue
Okay.
in more detail the next time. Okay.
Okay.
Thank you, everyone.
Okay, отлично.
Мгм,
Thanks
спасибо.
a lot.
Thank you.
Счастливо. Thank you.
Thank you.